welcome students in the lecture series of some basic concepts of real analysis. In the previous lecture, we discussed about properties of continuous function. We also discussed some naming theorems like boundedness theorem, maximum minimum theorem, location of roots theorem, Bolzano intermediate value theorem and their geometrical interpretations. In this lecture, we will discuss about uniform continuity and their properties. So, to understand the definition of uniform continuity, let us start with the definition of a continuous or recall the definition of a continuous function. So, let us start. Let A be a subset of R and a point C is a point of A. For a function f which is defined from A to R, we say that the function f is continuous at a point C if for any given epsilon greater than 0, there must exist a delta greater than 0 such that if we have x belongs to A and modulus of x minus c is less than delta, then we must have modulus of f of x minus f of c is less than epsilon. We say that the function f is continuous at a point C if and only if the limit of a function f is equals to f of c as x approaches towards c. Now, let us start uniform continuity. The definition of a uniform continuity says that if we have a set A which is a subset of R, for a function f which is defined from A to R, we say that the function f is uniformly continuous on a set A if for any given epsilon greater than 0, there exists a delta greater than 0 such that if for any 2 points, that is x belongs to A and y belongs to A, we have modulus of x minus y is less than delta, that implies modulus of f of x minus f of y is less than epsilon. I repeat the definition of uniform continuous function. We have a set A which is a subset of R and we define a function f from set A to R. We say that the function f is uniformly continuous on a set A if for any given epsilon greater than 0, there must exist a delta greater than 0 such that for any two elements, let us say x belongs to A and y belongs to A, satisfying x minus y is strictly less than delta, then we must have modulus of f of x minus f of y is less than epsilon. We must note that if a function f from A to R is uniformly continuous on a set A, then it is continuous at every point of the set A. But in general, however, the converse does not hold. If a function f from A to R is uniformly continuous on a set A and we have a set B which is a subset of A, then we can say that the function f is also uniformly continuous on the set B. The geometrical interpretation of a uniformly continuous functions. Uniformly continuous functions exhibit a uniform smoothness across their entire domain, whereas the steepness of the curve is bounded and does not become arbitrarily sharp. Geometrically, this means for any given error tolerance, say epsilon greater than 0, a single consistent horizontal width, say 2 delta, can be found to create a window, or we can say a box of a size 2 delta into 2 epsilon that fits around any segment of the graph, ensuring the graph does not exit the top or bottom of this box. Uniform window size. Unlike standard continuity, whereas the required, that means the horizontal precision, may shrink to near 0 at specific points, that is near vertical asymptotes. A uniformly continuous function allows the same to be used for the entire function domain. Bounded slope. If a function is uniformly continuous, it is generally cannot have infinite vertical steepness on a bounded intervals. The graph have vertical asymptotes or unbounded wingers. It must behave in a controlled manner throughout the entire domain. Now, let us start the definition of non-uniform continuity criteria. So, let A be a subset of R and we have a function f from a to r, then the following statements are equivalent. Our first statement is the function f is not uniformly continuous on a set A. Then the second statement is if function f is not uniformly continuous on A, then there exists an epsilon naught greater than 0 such that for every delta greater than 0 there must exist some point, say x delta belongs to A and y delta belongs to A. We can easily verify that this x is depending upon that delta, this y is also depending upon that delta. So, for there must exist some epsilon naught greater than 0 such that for every delta greater than 0 there are points, say x delta belongs to A and y delta belongs to A, such that satisfying the inequality like modulus of x delta minus y delta is strictly less than delta, and modulus of f of x delta minus f of y delta is greater than or equals to epsilon naught. I repeat the second statement, if we have a function f which is not uniformly continuous on a set A, then there exists some epsilon naught greater than 0 such that for every delta greater than 0 there are points depending upon delta, say x delta belongs to A and y delta belongs to A, such that we have modulus of x delta minus y delta is less than delta and f of x delta minus f of y delta is greater than or equals to epsilon naught. The third statement, which is also equivalent to the above two statements, this is there exists an epsilon naught greater than 0 and two sequences, say xn belongs to A and yn belongs to A, such that limit of xn minus yn is equals to 0 and modulus of f of xn minus f of yn is greater than or equals to epsilon naught for all n belongs to the natural number. So, if a function f is non-uniform continuous, then we can apply any these of three statements. The geometrical interpretation for a non-uniform continuous functions. Non-uniform continuous functions are continuous everywhere in their domain, but lack of bounded slope or a rate of change, causing the graph become arbitrarily steep or oscillating rapidly, often near vertical asymptote or at a large x values. Geometrically, for a fixed small epsilon greater than 0 and any width delta greater than 0, say hose or band around the curve fails to contain the entire graph, as points arbitrarily close horizontally still have outputs further than epsilon apart. Stepping graph, the slope of the function is not bounded. I repeat, the slope of the function is not bounded in the case of non-uniform continuous functions. If you place a hose or a width 2 epsilon around a non-uniform continuous functions, there will always be a part of the graph that escapes the hose, or regardless of how thin delta you make, the horizontal segment of the graph you consider. Violation of a small scale similarity. As you zoom into a non-uniform continuous function at different points, that is further out along the x-axis, the local shape of the curve changes dramatically. Now, let us start with some results based on uniform continuity and non-uniform continuity. Our first result is we have a set A which is a subset of R and a function f defined from A to R is uniformly continuous on A. Then the function f is continuous on that particular set. I repeat, if we have a uniformly continuous function on a set A, then that function is continuous also on that particular set. So, we need to prove that uniform continuity implies continuity. Let us start with the proof. Let I be a subset of R and consider a function f from set I to R which is uniformly continuous on that interval. We need to prove that f is continuous function on the interval I. So, for that let us say C be any random element of I. That means we need to prove that the function f is continuous at that particular point. That means by definition we need to show that for any epsilon greater than 0 there exists a delta greater than 0 such that if we have x belongs to I and modulus of x minus c is less than delta, then we must have modulus of f of x minus f of c is less than epsilon. Now, as given, function which is defined from set I to R is uniformly continuous function on the set I. That implies by the definition of uniformly continuous function, we have for any epsilon greater than 0, there exists a delta greater than 0 such that for any 2 points, let us say for any 2 elements x belongs to I and y belongs to I, satisfying modulus of x minus y is less than delta. That implies modulus of f of x minus f of y is less than epsilon. Say this is our equation number 1. Equation number 1 says that modulus of f of x minus f of y is strictly less than epsilon. Now, in particular taking y is equals to c, as we know that c belongs to the set I. So, in equation 1 we put the value of y as y is equals to c, we get modulus of x minus c is less than delta. That implies modulus of f of x minus f of c is less than epsilon for every x belongs to I. Then we get the definition of a continuous function at point c. As epsilon greater than 0 is an arbitrary element, that implies we can say that the limit of a function f of x is equals to f of c as x approaches towards c. Implies that function f is continuous at a point c, as we know that the point c or element c is an arbitrary element of the interval I or a set I. That implies the function f is continuous on the set I. Thus, we conclude that every uniformly continuous function is a continuous function. But note that the converse of the above theorem is not true. That means every continuous function is not a uniformly continuous function. That means we can say that if we have a function f defined from I to R is a continuous on I, then the function f need not be uniformly continuous on that set or that interval. To understand the converse part, let us start with the example. Consider a function f which is defined from I to R, where I is an open interval which is equals to 0, 1, and the function is defined as f of x is equals to 1 upon x. We can say that the function f is continuous on I, where I is equals to 0, 1 open interval, because being reciprocal of a non-zero continuous function. So, we can say that this function is a continuous function, but the function f is not uniformly continuous on this particular interval. Now, let us start with another examples. So, our example 1 is we have a function f which is defined from in a set I to R, where I is our closed interval say 0, 2, which is defined by f of x is equals to x to the power 4. Then the function f is uniformly continuous on that particular interval, that means closed interval from 0 to 2. So, let us start with the solution. As given, a function f defined from I to R, where I is our closed interval which is equals to 0, 2, and the function is defined as f of x is equals to x to the power 4. We need to show that the function f is uniformly continuous on that particular interval, that means 0, 2, closed interval 0, 2. That means we need to show that by mathematical definition for any epsilon greater than 0 there exists a delta greater than 0 such that if any 2 points x and y belongs to the interval I, which is equals to close interval 0 comma 2 and satisfying modulus of x minus y is less than delta, then we must have modulus of f of x minus f of y is less than epsilon. So, now let us consider the equation modulus of f of x minus f of y. As we know that the function f of x is defined as f of x is equals to x to the power 4. So, in similar way we can define f of y as y to the power 4. So, our equations become modulus of f of x minus f of y is equals to x to the power 4 minus y to the power 4. We can split as x square minus y square into x square plus y square. Again we can split x square minus y square into x minus y, x plus y into x square plus y square. So, we get modulus of f of x minus f of y is equals to modulus of x minus y into x plus y into x square plus y square. So, we get our this equation, and this equation holds for every x is greater than or equals to 0 and y is greater than or equals to 0. That means, the modulus of f of x minus f of y is equals to x plus y into x square plus y square into modulus of x minus y. We can take out from the modulus because x and y both are non-zero numbers, or we can say that both are greater than or equals to 0. And we know that x and y belongs to the closed interval 0 comma 2, as we can see that for every x belongs to 0 closed interval 0 comma 2 and y belongs to closed interval 0 comma 2. So, the maximum value for x and y can be 2. So, if we substitute these values here, we get modulus of f of x minus f of y is strictly less than 2 plus 2 into 2 square plus 2 square into modulus of x minus y. So, after calculating these values, we get our next inequality, this which is defined as modulus of f of x minus f of y is less or equals to 32 times of modulus of x minus y. And we can say that this quantity, that means modulus of f of x minus f of y is strictly less than 32 times delta if we choose modulus of x minus y is strictly less than delta. Now, we need to choose our delta in terms of epsilon. So, if we choose delta as delta is equals to epsilon upon 32 here, then we get modulus of f of x minus f of y is strictly less than epsilon. So, we are choosing delta as delta is equals to epsilon upon 32. Then for modulus of x and y is less than delta, we have modulus of f of x minus f of y is less than epsilon for every x belongs to the closed interval 0 comma 2 and for every y belongs to the closed interval 0 comma 2. Thus, we conclude that the function f of x, which is defined as f of x is equals to x to the power 4, is uniformly continuous function on the interval closed interval 0 comma 2. Now, moving towards our next example defined as we have a function defined from I to R, where I is in semi-open interval or a semi-closed interval defined as I is equals to a comma infinity, where a is a non-negative number, or we can say that a is strictly positive number, which is defined by f of x is equals to 1 upon x square. Then we need to prove that the function f is uniformly continuous on the interval a comma infinity or a semi-open interval a comma infinity. Now, recall the function. We have a function defined from f I to r, where I is a semi-open interval a comma infinity and the function is defined as f of x is equals to 1 upon x square. Now, let us start with the solution. So, given that a function defined from semi-open interval, that means a comma infinity to r, defined by f of x is equals to 1 upon x square and a is strictly greater than 0. We need to prove that the function f is uniformly continuous on the given interval. That means f is uniformly continuous function on the semi-closed or semi-open interval defined as a comma infinity. That means, by mathematical definition, we need to show that for any given epsilon greater than 0, there exists a delta greater than 0 such that for any 2 points x and y belongs to the given interval, that means semi open or semi closed interval a comma infinity, and satisfying modulus of x minus y is less than delta, then we must have modulus of f of x minus f of y is less than epsilon. Now, consider modulus of f of x minus f of y. As we know, the given function, the value of a f of x is 1 upon x square. In similar way, we can define the value of f of y as 1 upon y square. So, modulus of f of x minus f of y is nothing but modulus of 1 upon x square minus 1 upon y square. After taking LCM, we get as x square minus y square upon x square into y square. So, if we apply the formula of a square minus b square, we get a minus b into a plus b. That means, we get modulus of f of x minus f of y is equals to modulus of x minus y into x plus y upon x square into y square. And we know that x and y both are greater than 0, then we can easily take out from the modulus part. So, we get modulus of f of x minus f of y is equals to x plus y upon x square into y square into modulus of x minus y. For every x belongs to the semi closed interval a comma infinity, and for every y belongs to semi closed interval a comma infinity, and note that the number a must be greater than 0. So, from this we can easily generate our equation number 1, and equation number 1 says that modulus of f of x minus f of y is equals to 1 upon x into y square plus 1 upon x square into y into modulus of x minus y. Now, as we know that both the points belong to the semi closed interval a comma infinity where a is greater than 0, this implies that x must be greater than or equals to 0 as well as y must be greater than or equals to 0. So, this implies x square must be greater than a square as well as y square must be greater than a square. This implies that x square y must be greater than or equals to a cube and x y square must be greater than or equals to a cube. After taking reciprocal, we get 1 upon x square y is strictly less than 1 upon a cube and 1 upon x y square is strictly less than 1 upon a cube. After adding these two equations, we get our equation number 2. Equation number 2 says that 1 upon x square y plus 1 upon x y square is strictly less than 2 upon a cube. Thus, from equation number 1 and equation number 2, we get modulus of f of x minus f of y is strictly less than 2 upon a to the power 3 into modulus of x minus y. This implies that modulus of f of x minus f of y is strictly less than 2 upon a cube into delta if we choose as modulus of x minus y is less than delta. So, now we need to choose our delta in terms of epsilon. If we choose delta as delta is equals to a cube upon 2, then we get this inequality as less than epsilon. So, choose delta as delta is equals to a cube upon 2 into epsilon, then for modulus of x minus y is strictly less than delta, we have modulus of f of x minus f of y is less than epsilon. For every x belongs to the semi closed interval a comma infinity and y belongs to semi closed interval a comma infinity, for all a is strictly greater than 0. Thus, We conclude that the function f of x, which is defined as 1 upon x square, is uniformly continuous function on the semi-closed interval a comma infinity, where a is strictly greater than 0. In the next lecture, we will discuss some more examples. Thank you.